Okay, good morning, friends, or good afternoon, or good evening, whatever it is for you. We're here back for week 5, and this is day number 2. So, just a reminder, PLC 5 is here for Friday. We are going to start, well, we started a little bit of the diffraction stuff that this PLC is regarding. We started a little bit of that yesterday. Just a reminder that homework 2 is up for Thursday, and we'll have quiz at that point as well, and that will be the usual format. So take a look for those. In the meantime, let's go ahead and talk a little bit more about diffraction and what its consequences are, and how we are gonna how we're gonna think about the situation. So diffraction is different from the double slit situation, all right? Because ultimately we have to consider way more waves coming out. And I mentioned last time that this is the situation of kind of like multiple interferences, and that there's not really a difference between diffraction and interference, but there is just a lot more waves to consider, okay? So when we were thinking about interference, we said, okay, what if we've got these two sources and I have a wavelength that is, say, the distance from one white peak to another white peak here, right? I'm going to say, okay, if I have these two sources here and I have a screen kind of over near the ends, and where's my first constructive maximum occurring? Well, we're going to go until we get, oops, a little further up. We're going to go until we get another lining up when it hits a screen, right? So when it's hitting the screen, these white spots and these dark spots are all lined up again on these ones, not on the screen. They're all lined up again, and ultimately the same exact type of thinking is what we're going to use to try and analyze what goes on with a single slit, because in a single slit, we've got to think about, start with 3, we got to start thinking about multiple waves and what's going to happen now. I need 3 hands. What's going to happen now when I consider an interference between these 3 waves? Okay. So I'll come back to that. I'll try in the meantime to grow a few more hands and see if we can't figure something out here. But let's go take a look at the picture of a single slit. And I kind of drew this out for you a little bit last time. I'm gonna give you the same type of mentality that I gave with mirrors and lenses and these objects that we see images of. And I'm going to tell you, if you remember back to that, I told you that the object emits an infinite number of rays, because we were in the ray model at that point. It emits an infinite number of rays and an infinite number of directions. And when we draw those rays coming through the lens or bouncing off a mirror or whatever it was, we picked just a couple that were conducive to our understanding of what image is formed and why. Well, I'm going to tell you the same basic principle is at work here. In other words, if I want to think about what pattern I'm going to see on the screen and why, I'm going to choose a couple of waves to try and make the point such that I can draw out, say, oh, look, this is doing this is doing this, and that means, right, that means this is happening, okay? So make no mistake, for all practical purposes, there are an infinity of waves coming through a single slit. And They are, but that's just too many to count, right? They're all moving kind of towards the screen. They're spreading out. They're doing stuff. But in order to try and explain the behavior that we see on the screen, I'm just going to narrow it down and try to think about, okay, well, what do we need to look at in order to try and explain the behavior that we're seeing? Okay. So last time I drew you the picture of a couple of rays coming through here, a couple of waves coming through here. Okay, so imagine we're going to do the same thing here. I'm going to start with the waves at either side of the slit, and then I'm going to go to waves really close to the center. These ones are going to be right there and right there. All right, so when these waves go out from the slit, just as we talked about last time, these waves make a bright spot directly across from the slit because there is no path length difference between the waves, and therefore they all interfere constructively. And that gives you the bright spot. Okay. Now, if we go up at an angle, and I'm going to try and draw an angle up here, so we're going to look at, let's look at a place on the screen right about there, so that I'm going to look at that wave and then this wave coming from here. All right. And we're going to use the same basic approximation that we did with the double slit, which is, yes, I have interfering waves up here, which by definition means that they are intersecting. They are meeting there. However, I'm going to consider this such a small angle that we can initially consider these two waves as coming out along parallel paths. That is to say, if I took, looks like our light cut changed or something. Did we get dark? I don't know. If I took this and I covered up all of this stuff here, and I put all I let you see, I'm going to try to do this without erasing all my ink. All I let you see was that much. Would you say, well, those are pretty close to parallel? I mean, you can, well, they are. They seem pretty close to parallel, actually, when I'm looking at it like this. I didn't actually think that was going to work, but yeah, it does. If I look at only these little bits of the paths that the waves travel, that looks pretty parallel. So we're going to use the same approximation that we did with the double slit, in the sense that we're going to consider a path length difference and a set of parallel outgoing paths here, such that I could figure out how much more the lower one is than the upper one by dropping a normal down and finding out what that tiny little bit of distance is right there. Okay, so now that I've drawn the outermost rays, I'm going to draw the inner rays. I'm sorry, waves. I keep saying that. Too much time in the ray model. I'm going to draw these two. Now, these two are on either side of the very center one, or you might consider the center one's like kind of part of both of these somehow. I'm going to draw these as going right up in here, just like we would expect them to, because this is the way the light's going. And I've got this one, and I've got this one here. Now, okay, so now you might notice something. Gosh, I don't know about you. My screen seems really dark. And I'll tell you, it's because my battery just failed on the computer. So maybe the computer's still trying to charge and it's just not happy with the battery situation. Anyways, hopefully you're okay seeing that. If I take a look at these two paths that I just drew, and I guess it's kind of, can you kind of see that they're, yeah, you can kind of see that they're a little bit different. If I consider the path length difference between these two inner rays, would you say that's very large or very close to zero? I would hope you would say very close to zero. because these two are traveling almost the exact same, right? They're the almost exact same distance. They're so close to each other that for all intents and purposes, their path from this point on the slit or within the slit to over there on the screen is basically the same. That means that they are more prone to constructive interference, right? Okay, but let's think for a minute now. Suppose that I want to think about a dark spot happening over here. Let's suppose that I'm now going to impose a condition on the interference, and I'm going to say right up here is an interference minimum. In other words, it's destructive. It's a dark spot here. We are going to consider destructive interference. All right. So how are we going to explain that when I'm considering the paths of these two to be so similar that they might as well be constructively interfering? Well, in order to make this happen, what we're going to do is we're going to look at the path length difference of one of those waves with one of the waves out at the edge of the slit. In other words, I'm going to take this triangle right here and I'm not sure if you can quite see that one, but I'm going to blow it up over here so we can see it. All right, so it looks like that. This triangle right here is that triangle right there. As it was with the double slit, the exact same situation happening. I've got a right angle here because my upper wave, which is leaving from the very top of the slit, starts up at the vertex here and would be going that way. And the one that I'm considering, which is near the middle of the slit right here, has a path length difference of this much. Okay, this is the path length difference, and that means that this here is the angle at which they are leaving the slit. Okay, remember that we're considering essentially parallel waves leaving the slit. So that means that angle is the same as, for example, say I'm going to take this one from the middle. That angle is the same as this angle here, right there. Right, that's the angle away from going straight across to the central maximum. It's the angle up, just like it was in the double slit. Okay, this is the path length difference right here. That's the path length difference. Now let's be clear, that's the path length difference between what? Between the very first wave on the top edge of the slit, this one way up here, and then this one here that's just kind of towards the top edge of the center of the slit. Okay. I am going to call the distance from top to bottom of the slit, in other words, the width. This is known as the slit width. And it is typically called A, whereas the slit separation in the double slit was known as D. And also in the double slit, we considered basically 0 slit widths because we were only allowing through one wave at a time. Okay. Now we're widening these suckers and saying, okay, we're considering light coming through, right? And now that's where the infinity of light waves comes from. So if I consider the slit width to be A, then this distance here from this triangle here, I'm halfway down on the slit because this wave that I'm considering is basically at the halfway point down. So this is 1/2 A right here on that side. So if I want to calculate the path length difference, I do it the exact same way as I did it with the double slit. And I say, okay, I've got this triangle here. I know this this upper angle, I know this side, it's a right triangle, we have trig functions, and we can use them. So the path length difference here is going to be, in fact, that distance is the hypotenuse, so it's 1/2 a times the sine of the angle, and that's the path length difference. I'm going to then go through and do the exact same thing as I did with the double slit. I'm going to say, okay, if I have a dark spot here, then I had better think about this path length difference being a half a wavelength. Okay, I'm going to consider this to be not only a dark spot, but the first dark spot. Okay. Therefore, if I consider this destructive interference, that means I'm operating with m plus a half lambda in the path length difference. And if it's the first one, I should be saying that's 0, and it's really just a half a wavelength off. Therefore, down here, I would say 1/2 wavelength. All right, and this is for the first dark spot. And really, we are only going to be so interested in approximately the first, maybe the second, but you can go to other dark spots, and that's fine. You can do multiple second, third, fourth if you like. For this purpose, I'm just going to concentrate on the first one. So here in the single slit, the condition now for destructive interference, okay, we can see it's kind of falling out right in front of us here. So in order to find destruction in the single slit, we use this condition here, which is telling us that without the half on either side, A times sine theta is equal to lambda. Okay. So this is destructive interference in the single slit. And you'd say, well, wait a minute. That looks awfully like constructive interference in the double slit. Yes, it does. Yes, it does. And you'll have to make sure that you keep those separate. However, this is a single slit minimum condition. Okay, so what this does is basically it defines the size of the central maximum. Okay, the central maximum, which when you go straight across, right, would be, say, here. There's a bright spot here, but I got my first dark spot here. So what's happening between here and here? What's happening between there and there is that the intensity is getting lower and lower and lower and lower because it's on its way to becoming a dark spot. How do we think about this physically in terms of the waves? Okay. This is where the three hands are going to come in kind of useful here. All right. So what I'm going to do is I'm going to do this pairwise. Now remember, I told you last time that what often works well is because we have so much experience with the double slit is to just take pairs of waves and act like we're doing a double slit between those two. Okay. So what I have here are in fact, like I did last time, two sets. I have two pairs. Now, last time I drew them kind of evenly spaced. This time I concentrated on just the two that were right around the center point right here. So what I'm considering here is pairwise cancellation. In other words, if I take the outside edge rays and I go up here and I say, okay, look, there's a half wavelength between the outside edge rays. What that's going to mean is only those two are going to cancel, right? Only these two on the very far edges of the slit are going to be ones in which destructive interference is going to happen. Then when I start considering ones that are in here, in here, in here, in here, look what happens. I get almost constructive interference, right? When I separate them out back here to the edges of the slit, like this, one here, and I say, okay, look how it's matching up. It's destructive. I got the peaks here lining up with the troughs here, right? But as I start moving them closer and closer and closer and closer in, right, that path length difference starts to disappear. And now I'm talking about a lot of construction because these two things are almost lining up perfectly. So the condition cannot be that there's a path length difference of a half wavelength between the outer two waves. It has to be such that when I consider these middle ones, I cancel those, and then I move down a little, cancel those, and then I move down a little, cancel those, and I move down and down and down until I'm all the way down at the very edge of the slit, the bottom edge of the slit, and I've got cancellation here. I've got to cancel pairwise, okay? So that means I'm taking halfway, that's why this one half the slit width came in. I'm taking the halfway waves, and I'm canceling the halfway waves with the outermost waves. Right? And then, so if these two cancel here, this is the upper top of the slit right here, this is the center. If these cancel, then I move down a little bit and down a little bit, and then these cancel. And then I move down a little bit and down a little bit, and these cancel. Down a little bit, down a little bit, these cancel. So pairwise cancellation tells me that I have to only go half the slit in order to get half the wavelength, and that's how we deal with destructive interference in the single slit. Okay. Now, you might say, well, that doesn't seem right because if you have a wave right in the middle and that one cancels with the upper one, what's canceling with the lower one? Remember, there's an infinity of these things, okay? It's not just 1, 2, 3, and 4. There's an infinity of these. And so I'm just picking ones that are convenient for my understanding, okay? Okay, so this is how the minimum from the single slit is found. You might remember with the double slit that we did both conditions. We did the destructive interference with the half wavelength off, and then we did the constructive interference with the integer number of wavelengths, and then that giving you a bright spot. In the case of diffraction here, it's a little bit more difficult mathematically to find where are the actual constructive maxima. But it's easy to kind of just say they're halfway in between the minima. So that's what we're going to do. It just turns out that the mathematical description for that is a little bit more convoluted than we really need to be going through. Okay, so destruction in the single slit happens when there's a what this now boils down to is there's a full wavelength between the topmost and the bottommost waves in the slit. Okay, which, like I said, sounds kind of strange because it sounds like they would be constructively interfering, but in order to see the destruction, you have to kind of divvy up the slit. You have to divide it up into regions. Now, what if the path length difference between the top wave and the bottom wave was 2 wavelengths? Right? Would that still cause destructive interference? Is the question. If it was 2 wavelengths, well, what's so funny about that is that, yeah, it still does. So now when you want to go to the second minimum, and I was telling you we'll only concentrate on the first one, but I'll give you a little bit of insight on the second one here. If I go to the second minimum, now what's going on? Okay, if I've got 2 wavelengths between the uppermost and the lowermost waves coming from the slit, right? In other words, instead of just 1 lambda, I've got 2 lambdas here. Okay, that means the path length difference to the halfway point would be 1. And then that would louse up all of this, right? Well, yeah. But now you just find that there's a different wave you cancel with. Now you're going to look even further up and you're going to say, okay, I'm going to choose the 1/4 wave. There's a 1/4 wave that's coming out right here. And that one is a half wavelength out with the top one. And then the one close to that is a half wavelength out with the center one. And then the one next to the center is halfway out with the 3/4 one, and the 3/4 one's a half out with the lower one. So they all cancel still. All right? It's still pairwise cancellation, but you just divided up the regions a little bit more narrowly. Instead of doing half the slit, now I've done a quarter of the slit with a half wavelength, and that means I'm going to get 2 wavelengths in the path length difference between the outermost 2 waves. So, to generalize this situation, it's the exact same as the double slit constructive interference. And that really is just the way it is. So the general condition for destruction in the single slit is that A sine theta is equal to m lambda. And that is for destructive interference. So we're going to be able to, and I'm going to give you a couple of exclamation points. I'm not messing this up. This actually is how it goes. It seems like it shouldn't, but I think I wore my T-shirt of "Science doesn't really care what you believe." So there you go. It seems like it shouldn't, but it does, and there you go. So it's up to us to kind of mold our minds around trying to get an explanation for this. The angles are, again, such that we can consider them relatively small. And so when we go to looking at what the sine of the angle is, typically we don't calculate the sine of the angle because we don't know the angle, it's too tiny, but we can use the small angle approximation again, and we can approximate the sine with the tangent. All right, so the sine is approximately equal to the tangent, and the tangent, if you remember from the double slit, relates to the distance, which we called y, from the middle of the central maximum, and the distance to the screen was what I called capital D. So this is going to be approximately y over d, where the y depends on m. So I'm going to put a little subscript m on the y, because how far up you're measuring depends on what the order of the fringe is, just like it was in the double slit, right? So if I wanted the 4th bright fringe, I got to go 1, 2, 3, 4. That's further up than the 2nd bright fringe, which is just right there, or the 3rd one, which is right there. So my y value depends on the fringe number that I am interested in measuring to, and it's no different here. Therefore, we can say that on the whole, A times y sub m divided by capital D is equal to m lambda. And that would be your destructive condition using the small angle approximation. Okay. All right, so let's do a quick example of this, and just put some numbers into this and throw them around and see. Who cares? Let's see here. All right, I'm gonna just go right in here. All right, so let's see, I came up with a couple of numbers here, and so I said, okay, suppose that we've got a slit. We know the slit width. We'll just do a quick example here. We know the slit width is, say, 0.12 millimeters. All right, so 12 1/100ths of a millimeter is that's a pretty narrow cut. And this is kind of getting back to what I was telling you last time, which is that the more and more and more you try to narrow the light and squeeze it down into, I'm going to force you to pass through an even smaller opening here. The more you do that, the less it cooperates. I'm currently in the phase of parenting teenagers, so you can probably see how that relates pretty well. But I would almost say that this is true at any essentially any life stage, right? From except newborns, they're totally fine. They go with the flow. But once you get to toddlers, and then you start saying, and then you get to kids who are 5 and 10, yeah, it goes up and down, but there's always a little bit of that there. And then the teenage years come along. The less and less you try to squeeze light, the more it cooperates. The more and more you try to squeeze light, the less it cooperates. So the more you try to say, I want only one or two waves of light coming through, and you squeeze, the more spreading out you'll find, the bigger angular pattern you'll see on the screen. All right. So this is a pretty narrow slit. It's typical of slit widths. Let's suppose we've got a screen that's 1 meter away, capital D being 1 meter, and we've measured the distance. We've measured the spatial width of the central bright peak. All right, and we found that it's a certain number. But let me just draw. Excuse me. We found that it's a certain number. Let me just draw this on the screen here. If this is a dark fringe, if I draw the same type of intensity pattern as I did last time, right, I'm getting 0 intensity at the dark fringe here, and then maximum intensity right across from the slit. So if I say it looks something like this, right, then the other side of it would look something like this. And there's this large intensity, and it's not very symmetric, and it's actually quite yucky looking. Sorry about that. Make it nicer in your notes so that I get credit for drawing good diagrams, please. That would be great. The central should be right there, and I should be not drawing that. I should be drawing something more like that. Oh, that's not too bad. All right, dark fringes are occurring here and here. Right? Those are dark fringes here and here. And if we measure the width of the central maximum, can you see, I'm going to call this Y1. Can you see that, oh, whoops, Y1 is almost glared out. Can you see that the width of the central maximum is basically twice the distance that we would call Y from the middle of the central max to the first dark fringe, right? The width of the central maximum is basically the distance from the first dark fringe on one side to the first dark fringe on the other side. That defines how big the central maximum fringe is. So in this example, we measured the width of the central maximum. So I'm going to abbreviate all that and say we've measured basically 2y1. Okay? I'm just going to note here that this is this width of the central max. Excuse me. Another thing that teenagers give you. All right. So let's suppose we have these numbers, and I'm looking for what's the wavelength of the light that is passing through here in order to make that pattern on that screen. All right, so that's our goal. Well, it's nothing really quite so difficult, but we're just going to rearrange this thing to try and find out what the wavelength looks like. Now, the easiest thing is likely to just take half this number for your y value and note that because it's the central maximum, my index of which dark fringe I'm looking at is just 1. It would be 1 either side. So if I were to just apply this, I would say, well, I can calculate my wavelength pretty easily because m is equal to 1 at the edges of the central maximum. So y is just half this number of the 85. So it's 1/2 of 0.85. Now, in doing this, I believe I mentioned with the double slit, one of the main things to watch out for is get the units copacetic, right? And you can see the same thing's going to be true here. We're giving numbers in their conveniently measured units. And so it's up to us to try and get them all to work out nicely. So if I do centimeters here for the y, I'm going to do centimeters for the capital D, which was cited as 1 meter. So I'm just going to call that 100 centimeters. And so what that means is I'm going to be left with the wavelength in millimeters. Not super convenient, but it'll work. We're going to multiply that by the slit width of 0.12 millimeters. Okay. So this is going to be a pretty small number in millimeters, which it should be, right? Because millimeters, you're thinking about the wavelength of light, just off the top of your head, the wavelength of light visible, right, is somewhere between 400 and 700 nanometers. Okay, so that's a convenient set of, that's a bit of a fiction because 700 is a bit outside our range and 400 is a bit below our range, but it's a convenience. Okay, we'll just round them off nicely. But you're looking at hundreds of nanometers here, right? So if I consider, say, 500 nanometers, that's 500 times 10 to the minus 9th meters. So you can back that up to say it's 0.5 times 10 to the minus 6. So that's half of a micron, and that's still 1,000 times smaller than a millimeter. Okay, so you're expecting something that should be a fairly small number here. Okay, and so whatever this number is, you can calculate that, and hopefully it'll come out something reasonable within here and here. I don't seem to have a calculator with me, but nonetheless, there you go. All right. Good. So we've got that, we've got this, and I mentioned that past the first minimum here, we could go to the second minimum, and we could look at the second maximum as being halfway between the first minimum and the second minimum. And that's more or less pretty much the case. Like I said, the mathematics necessary to really show that are not really worth their while. So what I want to talk about here is the intensity of this pattern. All right, so what we've done, I want to kind of just take a step back here and think about what is it that we're doing. We're trying to describe the intensity pattern that we see on the screen. In other words, we want to know where are intensity maxima and minima, right? And with the double slit, we did that. We said bright fringe here, dark fringe here, bright fringe here, dark fringe here. We found all those. We located those fringes. We've done the same thing here, minus the bright fringes, but the dark fringes are, right, these That's going to help us locate the brights, which we'll say are halfway between. So we've done the location of the dark fringes and more or less the bright fringes, so good. But now we want to know how bright are the fringes that are located here and here and here as you go up and down the screen. And this is where looking at the double slit is going to kind of come back into play here. All right. So we're going to start looking at not just the single slit by itself, but we're going to overlay a single slit on top of the double slit. Now, why would we do that? Well, the reason is because when we looked at the double slit the first time, we had the slits so narrow that only one wave of light could get out of each one. And then we did that for our mental sake and not to try and keep track of an infinity number of things, but just to consider the interference between those two waves that emerge from the slits. Now we're going to take the double slit and we're going to widen these slits out. So we're going to make them finite wide slits. And we're going to have them be equal. There's a slit of width A here, and it's distance D away from a slit of width A down here. And we're going to look at what does the pattern look like now. Okay. So to do that, what we need to think about is, well, how do we consider the intensity? How do we predict and calculate what the intensity is going to be on the screen based on the light coming through the slit or slits? Okay. So let's go back to the central maximum here real quick. All right, let's go back to the central maximum, straight across. That should be really bright. Okay, that should be really bright. It is really bright in the double slit too, because with the double slit, the waves were coming out. They had essentially zero path length difference, and they were interfering constructively at the central maximum. Now, when we considered the secondary bright fringes, the ones that were not the central maximum, when it's double slit situation, we find that those fringes were almost as equally bright as the central one, just by looking at the pattern. This was the Dr. Teeth pattern that I was referring to last time. When I consider the single slit setup, that is not the case. We find the central maximum is very bright, as you'd expect, but when I look at the secondary maximum, or one that's up here, right, it's much dimmer than this one. And so when we overlay these patterns on one another, we get to be able to describe the full double slit intensity pattern. All right, and so that's what we're going to try and start now, and I'm not sure if we'll finish today or not, but we will give it a quick try here. All right. So all right. Pardon me. Okay, so let's take a look at the central maximum and the bright fringes of the double slit. And then we'll come back to the single slit and take a look at the intensity patterns of that. Okay. So we'll go here. Oops. Okay. All right. Battery's low again. All right. Everything seems to have low battery. All right. Why don't you come over here, and we'll do that. Okay. Let's go back to the double slit. That's what we were going to do. And let's analyze the intensity pattern. got a screen out here. All right. So if I were to sketch the intensity of the light as it impinges on the screen, then we would say I've got a peak that's probably, say, here, right? And it's kind of the situation where you're looking at it right like this. I'm going to say intensity goes up this way. We'll do this in blue. Right, so this is like the intensity axis. I go straight across. All right, something like this. I'm going to try and plot the intensity as a function of where on the screen we are. So you'll notice that the central bright should be quite big, and lo and behold, it is. Okay, like so. And that is a little bit lopsided. I don't want it to be too lopsided. Pardon me. So here's our central bright fringe, and we go to the first dark here and here on either side of that, and we go to the next bright fringe like this. All right, so what we're noticing is that the intensity does not actually diminish due to double slit interference as the angle goes up or down, away from the central maximum. At least I tried to make it that way. They all hit pretty much the same size. Okay, so one of the things we want to figure out is why is that? All right, so what's the intensity pattern of the two slit? Well, when you think about the waves that are coming out, and we think about how they interfere and what that means. Okay. What we're going to find is that the peaks lining up with peaks, right? I have only two waves. So when the peaks line up, I get construction, and that means it's a maximum in the amount of energy that's going to be located at that point on the screen. So when I go up here and I go, oh yeah, look, oops, okay, look at that, I've lined them up again. At that point on the screen, that means I'm getting a maximum in the amount of energy. Well, that maximum would be the same every time because the condition of having a constructive interference bright fringe is that the peaks line up, right? In other words, these peaks always line up with one another. They're always like this, or like this, or like this, or like this, right? So as long as the peaks line up with one another, then what I'm adding are basically the same amount of intensities every single time. All right, so the peak intensities let's look at the peak intensities. Suppose that I consider that I'm getting an intensity coming through here of I not leaving that one and I not leaving that one. All right, so in other words, whatever the light is that I'm shining, If I have just one consistent laser light out here that's shining through, it's the same intensity leaving both slits. Okay. Now, here's an interesting piece to think about, and that is when the two waves destructively interfere. Okay, here, for example, here. When the two waves destructively interfere, does that mean that there's no energy? Because light is definitely hitting the screen at this point. It has to be. It's destructively interfering though, so what's happening with the energy that is coming out of the slits? What's happening with the energy at this point? Well, the energy is getting destroyed. Ooh, I just used a sentence that we're not supposed to use, right? Uh-oh. Okay, so there's no energy here. If I have a meter, if I have a sensor, and I got my light sensor and it's right here on the screen, it's registering a lot. If I move it here, it's registering less. If I move it here, it's registering 0. So there's literally no light energy hitting this point right here on the screen, or this one up here. How can that be? If light carries energy and light's hitting every point on the screen, how can the energy not be there? Is the energy literally getting destroyed? Well, no. No is the short answer to that, and you know it has to be, right? Because it's gotten drummed into you from early days in your 4A class or whatever you took, that energy is always conserved. And you cannot create nor destroy energy. And there's people who write this down and say, whoa, 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 whoa. Well, okay. What happened to it then? Well, what we're finding is actually it's getting redistributed. It's not that it's gone, it's just that we've put it somewhere else. Well, we haven't done that. The light did that for us. Okay, in the sense that if I consider the size of the peak here, right? If I consider the size of the peak, how much intensity is getting to the central point, or any of these bright spots? How much energy is getting, not energy, I should say intensity. What intensity of light is arriving at this point on the screen? Well, we've always said it's a maximum, and hey, that's great, but how big is it? It turns out that it's not 2 I naught like you might think it would be. 2 I naught is halfway. This peak is actually 4 I naught. Okay, this line right here is actually 4 I naught. Okay, and the reason for that is what I was just saying. The energy is not disappearing, it's getting redistributed. Okay, in other words, light is taking the energy that's coming through and saying, no, it's not going to land there. None of it's landing there. I'll put some of it here and then a whole bunch of it here and then some of it here, but none there. I'll put some of it here, a whole bunch there, some of it here, but none there, as you go through all these bright fringes and dark fringes. Okay. So what we want to think about is, how do we show this? Can we show this mathematically? One way to do it is to think about the relative phase of the waves, right? In other words, mathematically, how do we add a crest to a crest, or a crest to a trough? How do we do this? All right, well, what we were going to do is we're going to say, all right, let's consider the phase of the wave as it leaves the slit and arrives on the screen, and let's consider comparing that phase to the phase of the other wave when that hits the screen. All right, now, with the central maximum, you'd notice, and I kind of used this analogy before when I tried to show the bicycle wheels, if I consider the top wave here and the lower wave here as coming through with the same initial starting phase in their cycles. If I consider the central maximum, then I would say, well, if these waves acted like wheels, then they would have just rolled through the same angle by the time they got here, and they would still be in phase, right? And then you'd say, okay, what about one of these things? Well, now, I'm going to go to the lower one here. Now, what happened is the upper wheel here rolled through a slightly longer, and they hit. And they were both like this, okay? Whereas when I consider a dark spot, I'm getting them to roll, and that one lands like this. And now they're pointed like this when they hit the dark spot here. So the question is, can we kind of identify that mathematically? So in order to do that, I want to introduce a phase angle. Let's do this. I want to introduce a phase angle, and that phase angle is the phase difference between the two waves, okay? Such that if the phase difference between the two waves is 0, then I'm getting a maximum bright fringe, right? All right. So let's think about this difference in phase. All right, so when the phase angle is, say, 0 or 2 pi or 4 pi, we get maximum intensity. All right. Okay. So I see that I'm just about probably going to need to be running out of time. I'm just about running out of time. So we'll pick this up tomorrow. But the idea here is that if you want to think about the function which is going to be maximal at these points, right? Well, wouldn't that be the cosine? That looks like a cosine. That's going to be a big. It's going to be at its maximum when the phase angle between these things is that, right? So if we're thinking about a cosine, right? Isn't that kind of what this looks like? If I just kind of chopped this half of it off and looked at this, starts up high, dips down, goes up high again. Yeah, that looks like a cosine. So we're going to be interested in thinking of the intensity pattern as related to the cosine of the phase angle of the phase angle between the two waves. Is proportional to cosine. And in fact, because the cosine normally would have dipped below the axis and come back up, this is always above the axis. It's a square. So this is really cosine squared of an angle, which I'm going to call beta, cosine squared of beta. So we're going to pick this up tomorrow, and I will talk about the emergence of the cosine squared pattern from analyzing the phase difference between the waves as they leave the slit. And then what we'll do is we'll roll back to the single slit and do the same thing. And then we'll just put those two things right on top of one another, and we'll look at the full intensity pattern of the double slit as it is affected by both the two slit and also by a finite slit width. In other words, the single slit pattern. But I'm going to leave it here today and pick this up tomorrow. And I will wish you a happy rest of your day. Hopefully you are surviving week 5. We're just about halfway through. So good luck, and I will see you tomorrow. And then Friday we will have lab, and it will be on interference. And hopefully you'll have a little bit of fun with that, because in your lab kit you should find some combs which have very narrow slits, and we're gonna make use of that in trying to fabricate some double slit and some single slit setups. So look forward for that on Friday, but until then we'll have class tomorrow, and I will see you then, folks. Take care.